And let's start out by talking about what the idea of resonance even is. Because I think this is probably the first time you've ever heard this word, and it can be a little scary at first. Okay, so hey, let me give you a little background on the story behind resonance, and then we'll talk about how it works. Okay, so hey, resonance is a relatively new idea in chemistry. When OChem first started out, there was no such thing as resonance. Everyone was just drawing out one Lewis structure for each compound and life was good. It wasn't until we started messing around with more complex compounds that we realized that a single Lewis structure is insufficient to describe some compounds. So let's go ahead and write that down because that is the whole idea behind resonance and resonance structures. Which, by the way, you don't know a thing about just yet, but you will in a second, okay? I'm just giving you a little history first, all right? So, hey, this was the deal. A single Lewis structure was insufficient to describe some compounds. Okay, so this says, exclamation point, a single Lewis structure is insufficient to describe some compounds, okay? Therefore, we have resonance structures. That's why we came up with these things called resonance structures. So what the heck are resonance structures, you guys? Okay, so before I give you the technical definition, I always like to intro this concept by telling you how I think about resonance structures. And drawing resonance structures is kind of like portraying faces of human emotion. So let's write that down. Okay, so for example, drawing resonance structures, this is kind of like portraying faces of human emotion. Okay? So what this means is, if someone asked you to draw what human emotion looked like, how would you draw it? Would you be able to draw human emotion in just one picture? Okay, well, if you think about it, there's at least three basic parts to human emotion. People can be happy, they can be sad, or they can be whatever, right? Right? So, hey, I'm thinking you need to draw at least three different pictures to adequately convey these emotions. So, hey, if someone asked me to draw emotion, I'd draw a happy face, a whatever face, and a frowny face, right? Okay, and these three faces taken together as a set accurately represent emotion. Oh, and do me a favor, draw brackets around these three structures. Let me draw this one a little bit further to the right to further separate this guy. Okay, cool. So do me a favor and draw these brackets around these structures because this is what you need to do for resonance structures later, okay? And also draw double-headed arrows between these faces, and you'll see why in just a little bit. The point is, you guys, if you were to take these structures separately and try to represent emotion, you couldn't do it. It wouldn't be accurate. A happy face by itself doesn't convey all emotion. A frowny face by itself doesn't convey all emotion. And a whatever face by itself especially doesn't convey all emotion, right? You need to draw all three to accurately represent emotion. So, hey, star, right? You need to draw all three to accurately represent emotion. All right, so let's see an actual example of this, you guys. So let's erase this theoretical happy face, frowny face example. And let me show you an actual example. So let's take CO3 2- for example. CO3 with a 2- charge, for example, okay? So hey, CO3 2- is a perfect example and one of the original compounds we worked with when figuring out resonance. So let's go ahead and draw out the Lewis structure for this guy just like we would for any other compound, okay? And if you follow the rules for drawing Lewis structures that I listed out for you guys in our last session, you should end up with something like this. So a C double bonded to an oxygen, single bonded to two oxygens, with a negative charge on both of these single bonded oxygens, okay? All right, so let's make a quick note about this guy because, hey, this drawing implies that one oxygen is different from the other two, okay? So, hey, this drawing implies that one oxygen is different from the other two. Okay, because if you look at this, you guys, it looks like this oxygen on the top is different from these two oxygens on the side. This oxygen on top has a double bond. Okay, these oxygens on the side only have single bonds, right? Also, this oxygen on top is neutral. These oxygens on the side have a charge of -1, implying that this oxygen on top is different from these two oxygens on the side. And hey, you guys, this could not be more wrong, okay? So, hey, let's write that. This is really wrong. One oxygen is not different from the other two. Okay, so 3 exclamation points. This is wrong because, hey, experimental evidence shows us that all 3 of these oxygens are equal. So, hey, experimental, EXPTL, experimental evidence shows us that all 3 are equal. Shows that all 3 are in fact equal. And this was based on 3 undeniable pieces of evidence. Here's the first piece of evidence. Okay, the first piece of evidence was that each of these oxygens have the same bond length. Okay, so, hey, same bond length. All right, so hey, experimental evidence shows that all 3 of these oxygens have the exact same bond length to this carbon. If there were in fact 2 oxygens single bonded and 1 oxygen double bonded, like we see here, we would have measured different bond lengths because we all know from GChem that a double bond is shorter than a single bond. So this double bonded oxygen should have been 1 bond length and these single bonded oxygens should have been another bond length, right? But this was not the case. All 3 of these oxygens had the exact same bond length to this carbon, proving that this Lewis structure alone was inaccurate, okay? So the second piece of evidence was that they had the same basicity. Each of these oxygens have the same basicity. Let's write that down. Same basicity. So experimental evidence showed that each of these oxygens had the same basicity, meaning that they all pick up hydrogens at the same rate. And if you don't understand what that means, don't sweat it. We'll get to it when we get to the acids and bases chapter. But the point is, you guys, these oxygens proved to be the same again on this account, which again proved that this one Lewis structure by itself was inaccurate, okay? So hey, if that's still not enough to convince you that each of these oxygens are the same and that this one Lewis structure is inaccurate, I've got a third piece of evidence for you, okay? So hey, the third piece of evidence that these are the same is that they have the same negative charge on them. The same negative charge. This one Lewis structure implies that 2 oxygens have a full negative charge and 1 oxygen has no charge at all. But experimental evidence showed that each of these oxygens had the same amount of negative charge. Okay, so after these 3 pieces of evidence, you guys, chemists all had to agree. They all agreed that you must draw multiple structures for accurate representation. Must draw multiple, as in more than one, multiple structures for accurate representation of the compound. Okay, and these multiple structures later became known as resonance structures. Okay, so, and let me put AKA, these later became known as resonance structures. Okay? Okay, so let me erase this real quick, and I'm going to put up the resonance structures for this guy, and then I'll explain how you do it, okay? Okay, so this guy had 3 resonance structures, and notice, I put double-headed arrows connecting each of these resonance structures, and I enclosed the entire set in brackets. This is how you draw resonance structures, okay? So hey, this guy had 3 resonance structures. Some compounds have more, some have less. It just depends on the compound. But let's point out a couple of things here, okay? Alright, so let me just shrink down here real quick. If you look at this first resonance structure, this is the one I had on the board before, right? Okay, well, we said that this was inaccurate by itself because one oxygen looked like it was different from the other 2, right? We said it looked like they differed in charge and bond length, which experimental evidence told us wasn't true. So let's look at how these 2 other resonance structures try to make amends for this and show that all 3 oxygens are actually the same, okay? So, hey, in this first resonance structure, we see that this oxygen on top is neutral and these 2 on the sides have a negative charge. But if we look at the second resonance structure, you'll notice that, hey, now the oxygen on the top and left have negative charges, but the one on the right side is now neutral. And hey, if you go on to look at the third resonance structure, you'll notice that, hey, now the oxygen on top and right have the negative charge, but the one on the left side is now neutral, okay? So, hey, by drawing out all 3 of these resonance structures, we have shown that each of these oxygens gets an equal chance to be neutral or have a negative charge. If you look at them as an entire set, they no longer imply that one oxygen is different from the other 2. They are all in fact equal. And if you look, we did the same type of thing with the double bond, okay? Every oxygen gets an equal chance to have a single or double bond. In this resonance structure, this oxygen gets to have the double bond. In this resonance structure, this oxygen has the double bond, and in this resonance structure, this oxygen has the double bond, okay? These resonance structures are just trying to show you that all 3 of these oxygens are the same. They have the same bond length and same negative charge, which is why you may also see a professor or your book draw this compound like this, okay?